7.2 had a bunch of calculations in it, which are annoying. It was like the standard deviation calculators and stuff like that to do the probability distribution. So I found a website. I just posted it on my website too. So it's on the post 472. So you can use this to do that. So let's look at like this one and I'll show you how it works. It's pretty simple. So this is the number of errors and that's the probability of each. So first thing, is it a probability distribution? Is that a probability distribution? What are the criteria that it has to meet? Everyone's between 0 and 1. So is it everyone between 0 and 1? And what's the second one? It has to add up to 1. Does this add up to 1? Point 0.02, 0.05, that's 0.3. Yes, it does add up to 1. Okay. I know, I did it a couple of times too. Yeah. All right, so this adds up to that. So basically what you do is you take each of those, the X values, and you put them in the first list. You put the probabilities in order in the next list with commas, and you tell it what you want. The same order. No, the same order. So 2 goes to 0.02, 3 goes to 0.25, 4 goes to point. So they have to match up. Okay. And then let's say we want to find the standard deviation. So click standard deviation, and it finds the standard deviation for you. Okay. So that should save a ton of work on that section. So, okay. All right. You're welcome. All right. So the first thing we're going to look at is literally going to be quick. We're going to be done with this in like 5 minutes. Is the discrete uniform distribution. When you think of something that's uniform, what do you think of? They're all the same. And that's exactly what a discrete uniform probability distribution is. It is literally something that they are all exactly the same. So if you roll a die, 6-sided die, each of the probabilities is exactly the same. They're all one-sized. Okay. If I was to roll 2 die and find out the sums, is that a uniform distribution? No, because some other number, like 1 and 12 only comes up once, but 7 comes up 6 times. So it's multiple things there. So that would not be uniform. Okay. All right, let's do one problem with this one. And I picked one that did not have to do with coins and dice and everything else. So it's a little wordy. Charlene, this is put down payment on a small lot in a subdivision. There's 10 lots in the subdivision, and they're all approximately 0.25 acres in size. 5 builders have been contracted by the subdivision manager to build 2 homes in order to finish the subdivision in 6 months. Charlene's uncle is one of the builders. What's the probability that Charlene's uncle will be the builder that builds her house? So we have 5 builders, right? So we're going to call them, if my thing lets me write. So we're going to say it's 1, 2, 3, 4, and 5. And we'll call Charlene's uncle number 4. What's the probability? So first off, how many lots are there? 10. How many is each one doing? 2. So it's 2 out of 10, which is, what's the reduced of 2 out of 10? 1/5. So that's 1/5. 2 is going to be 1/5. 3 is going to be 1/5. 4 is going to be 1/5. 5 is going to be 1/5. Is that a probability distribution? Or are they all between 0 and 1? Do they add up to 1 if you add them all up? Yes. Okay. What's the probability that Charlene's uncle is going to be the builder of her house? 1 in 5. 1/5. That's the answer. Okay. So now, the vast majority of things are not going to be uniform probability distributions. They're not going to be all exactly the same. Most situations do not come out that way. So, but if they do, it makes life a lot easier. Congratulations, we're done with that one. Moving on to the actual meat of today's lesson, the binomial distribution, which is what I said. This is what, so if you're having trouble with 6-4 still, some of the questions started bordering on this process, which will make your life a little bit easier to deal with. Okay. The binomial distribution. It is a process that allows us to find the probability of an event happening out of a certain number of events. So if I wanted to find, for example, the number of heads, and I toss a coin 4 times, I want to find the number of heads I get, I can use the binomial probability distribution. What's the word binomial mean? Because that's going to be the big key in this process. 2. Okay. That means there can only be 2 possible options. All right. So rolling a die would not work because there's 6 possible options, right? However, if I said, what's the probability of me getting a 6? That would be fine because my options are 6 or not 6. Okay. The probabilities won't be the same, but that's not a problem with this process. This is not uniform. So when we're looking at the binomial distribution, we're looking at something that has basically 2 possible options. What I wanted. That's right. All right. So binomial experiment. These are the keys. It needs to fit these 5 things for it to work. The first one is there's only 2 outcomes: success and failure. The experiment can consist of as many numbers of trials you want. However, they all have to be exactly the same. Okay. So flipping a coin. You can't go, okay, on the first 10 trials, I'm flipping a coin. The next 10 trials, I'm flipping a dollar bill. Those would be different things. Okay. The probability of success of any one trial is denoted by P. That's the probability of success. The probability of failure would be then 1 minus P, because that's the exact opposite of it. So in my example of the dice, if I want a 6, what's my probability of success? What's my probability of success if I just want a 6 on a die? 1 out of 6. That'd be the success, right? What's the probability of failure? Huh? 5 out of 6. Okay. Your success and your failures have to add to what? Your success and failures would have to add to what? 1. Okay. They have to add up to the 1. The next thing is the trials are all independent. We talked about independent and dependent, right? Independent events do not restrict each other. Okay. So if I'm taking a card out of a deck, I'm putting the card back into the deck and taking the next card out of the deck. Okay. So they don't impact each other. And the binomial random variable is the count of the number of successes and the number of trials. So what we want to know is how many successes we have. Okay. Questions with any of that? Everybody got that down, so if I switch the page in a second. Okay. This is our formula. As with all formulas, I'm going to show you an easier way to use this. Okay. My formula is right up here. That's really the only thing. That's my formula right there. We don't need to worry about this piece here. N is the number of trials. P is the number of the probability of success. And X is the number of successive trials that I want. And actually, yes, it is N minus X. You're welcome. Really? Computer is very glitchy tonight. I don't know why. Sorry, those in the meet. Give me a second, because it's going to kick me. There we go. Okay. All right. Here's how we're going to make this one easier. You're going to use Desmos. Huh? Yes. So in Desmos, you can type the formulas into it. So that is what I just did. So on that first line, I typed the exact formula in that was just on the screen. NCR, N comma, sorry, they used X, N comma X. And then it's P to the X, 1 minus P, N minus X. Okay. So this right here, you're telling you how many choices out of that you're going to have. The P to the X is the probability times how many successes you want. 1 minus P is going to be the probability of failure and how many failures you're going to have. On the next three lines, put N equals, X equals, and P equals. Because now what I can do is I can fill in my numbers. So 5 out of, or not 52. Yes, that is the binomial probability distribution. And you can type the numbers in, and it'll give you your answer up here. And then you can just change these numbers to whatever numbers you need for the next problem. I have not found a way to save it. So in the graphing calculator, you can save things. In the scientific calculator, it doesn't let you save things. All right, so here's the problem we're going to do, and then I'm going to go back to that and put it in. We're going to toss a coin 4 times. And I want to record the number of heads. Okay. So, is this a binomial distribution experiment?
Yes.
Okay, I have the success is what? Heads, failure is tails. So, okay, so I have that. All right. I'm doing it 4 times. It is a similar experiment each time. So this meets that binomial random variable thing. So what is my N? In this case? I'm tossing coin 4 times, right? Okay. Am I missing something in this problem? Hold on. Oh yeah, it didn't actually tell you. That's fine. All right. I want to find the probability that I'm going to get 3 heads. Okay. So what's the probability that I'm going to get 3 heads out of 4 problems? I want to find something.
This thing's on down, but
Oh, I just wanted to have 3 heads. I gave you that answer. I gave you that number.
so you can just stop.
Well, in this problem, they didn't tell you because there was a bunch of other questions for it. I'm actually going to do the problem you sent me the other day in a minute. Yeah.
Oh, got it.
Because that's why I said, I'm like, that question fits this better than the other thing. All right, so I want 3 heads. What is my probability of success? What's the probability that I get heads on any one throw? 1 out of 2. Right? Okay, so I want to know what's the probability of me getting 3 heads out of 4 tosses. And this is exactly 3 heads, not at least 3 heads. This is exactly 3 heads. Okay? Everybody understand where those 3 came from? Because now I'm just literally going to type those into the formula thing that I just got, and we're going to get our answer. So we got 4, 3, and 1/2. We type in 4, 3, and 1/2, and the probability of getting exactly 3 heads is 0.25.
Mine is not good.
Make sure your letters are exactly the same. Click function is very, very bottom of it.
Wait, no, I think I know what I did.
Okay.
Yep, I got it. Never mind.
Everybody else fine?
I just forgot the comma between
Uh,
the
yours?
You did exactly what I did. Add a comma. Yes. And then you add- yes.
I think that one, you actually have to type the number in first. So you're going to do 4, hit that button. Yeah. You're going to put 4, that button, and then 3 on that calculator.
What was the?
3. They used X.
So I've learned all that.
All right. So here was the problem that I got sent the other day. All right. So how many ways can a person toss a coin 8 times so the number of heads is between 4 and 7? Oh, I didn't switch over. There you go. All right. So same process. It's fine because you literally took it with your phone on the screen. I literally just copy and pasted. All right. So we need the same things. We need N, X, and P. It's a cost of a coin, so P is still 1/2. In this case, it was 8 times, so my N is 8. And they want between 4 and 7. So X is going to be 4, 5, 6, and 7. So we have to do this problem 4 times. Probability of getting heads is 1/2.
What's the title of what we're solving for?
Binomial distributions.
Okay.
So binomial distribution helps you find the probability of an event occurring.
I'm having a shortened title so I can put,
Yeah.
something equal.
All right, so 4, 5, 6, and 7. So we have to do this one 4 times. So I'm going to do x equals 4, x equals 5, x equals 6, and x equals 7. So we're going to go over to use the calculator. I'm going to do the exact same thing 4 times. The nice thing is, so here's my x is n is 8, my x is 4, my p is 1/2. So I get, we'll do 3 places. So 0.273. And why Desmos is so nice to use? I just have to change the x. Now, on your calculator, if you hit second, was it? There's a thing you can hit that'll literally put the problem right back on your screen. So then you can just go change the number in it again. So you don't have to keep typing it in again. So 5 was 0.219. 6 is 0.109. And 7 is 0.031. And then what do you think we do to those? We add them up.
What was the first one?
Yeah, 0.273. Oh, and no, that's actually in here. Yeah, that's in there. So don't put that. That's the mistake. Yeah, that's the mistake. So we're going to add these 3 together. And we get 0.632. So that's the probability of getting the number of heads between 4 and 7 inclusively. So. Right. They wanted you to do this out by listing out all the possibilities and counting how many of them there was.
So could I put that answer in and it should be correct?
It should be correct, yeah.
I don't remember how I did that. I did it like an hour ago. And I couldn't tell you how I did it.
That's why when she sent me it, I'm looking at it, I'm like, that's a binomial distribution. And then I'm looking at it, I'm like, I'm sitting there trying to explain to her how to do it without it, and I'm like, I can't. And then I got a new phone and totally forgot about the text. Sorry. Yeah, sorry.
It was like, I did the CNR 3 times or something.
Yeah, because I originally got the first half of that.
Or no, the one of those things I did multiple times, and then I just added it together and divided it. Or something.
Yeah, it happens.
Really weird.
It's like
I couldn't tell you what I did.
you probably did something very similar to what we just did, not realizing that's what you were doing. So, but that's how you technically would do
I
that problem.
didn't have a simple formula to plug in.
Correct. Now you do. That's why I said, I'm like, we're going to do this later on. I don't know why it was that early.
NCR, that's
Yeah.
NCR.
All right. Let's look at this one because I want to do a few that are not necessarily coins and dice and stuff like that. Because while those are really easy to use, not useful for you in real life. Like that's not where you're ever going to really use it unless you're just constantly playing games. So it says, according to a recent national poll, about 40% of Americans believe in ghosts, which I thought this was apropos for being October and Halloween variant. Assuming this percentage is accurate, if 20 people were randomly selected and asked if they believed in ghosts, what's the probability that 12 or more would say they do?
Are
Okay.
you taking that as 40% or 40 out of 100 at first? Or are you saying as 40?
It's 40%. And I'm actually going to change this problem because I don't feel like doing this like a million times. We're going to say that exactly 12 believe in ghosts because I don't feel like doing this. Because to do the problem as it is, you'd have to do 12, 13, 14, 15, 16, 17, 18, 19, and 20. So I don't really want to do that. I will show you one in a second with this one that we can do the other direction though. All right. So first thing we need is our 3 pieces of information. We need N, we need X, and we need R. Not R, P. They use X instead of R, and it's screwing me up. How many people did we look at? So that's my N. How many people do we want? That's my X. What's the probability that they would believe in ghosts? 40%.
Oh,
So my probability is 0.40. Okay. Probability is always going to be a decimal because it's got to be between 0 and 1. And there's the 0.
he's like, I've been trying to get on for like.
Yeah, it's if you scroll back, it is on the page, but he just sent me an email. Well, he sent me an email like 5 minutes ago. I just happened to notice the little dot. All right, it's fine. All right, so we're going to go back over to Desmos. We still have my formula there. We're going to change N to 20. We're going to change X to 12. And we're going to change this to 0.4. So the probability that I would have exactly 12 people believing in ghosts is 0.035. And that would be my probability of exactly 12 people out of the 20 believing in ghosts. So 3.5% would be the chance. If we change this to 3, it goes down to 0.1, 13, 14, 15, 16. You can start seeing how now it's getting down to like, so basically after you get past 15, we don't even have it to 3 decimal places anymore. So at 16, 17, 18, 19, and 20, you basically could say it's pretty much a 0. Even though it's not exactly 0, it's pretty close. Okay. If you have the book, or if you look at the ebook, if you go down to Appendix A and E, which is your binomial probabilities, it has the binomial probabilities already done for the whole number. So 1 to like 10%, 20%, all the way up to 90% for each of the things. So you could have gone down to, in this case, this was 20, right? It was 20 people. So you could have gone and scrolled down. It goes up to 20, actually. All right, and we had 0.4, so this is 1, 2, 3, 4. And you could have then just added the 12, 13, 14, 15, 16, 17, 18, 19, and 20 together to get the answer there too. So it's got a table in the back of the book that has all those broken down for you. As long as it's an even, like the the 10% probabilities. If it was 15, you couldn't use this. Or if it was 42%, you couldn't use this. But the basic ones are there for you. All right. Let's say I wanted the same thing, but we're going to do the same problem. But I wanted less than or more than 3. Or 3 or more, I should say. 3 or more. Okay. So I'm still going to look at 20 people. That's still 40%. That's still the 40%. But I don't want to have to do 3, 4, 5 all the way up to 20. I can do 0, 1, and 2 instead. If I did 0, 1, and 2, what would I then do to find my final answer? Because I'm finding the opposite of what I want, correct? So take your answer you get from there and subtract it from 1. And it'll give you the opposite.
You've got copy that 0.035 minus 1. That's a whole new number.
No, it's a whole new number entirely. So if I use my the little chart, the cheat sheet that I told you about a second ago, so I don't have to use the formula for it real quick. See how this works. So we're going to then go, and I want 0, 1, and 2. So we're going to add those 3 together. So 0, they did to 4 places, so 0.0036. And I would do 1 minus that, which would give me 0.9964. Would be 3 or more. So instead of having to do all the values, if sometimes it's easier to do the opposite of what they gave you. Okay. Does that make sense? All right. Expected value and standard deviation. Don't worry. These formulas are way easier. And it's only using the letters you already came up with. It's only using N and P. So your expected value is just N times P. So in the last problem, I had N was 20 and P was 0.4. So my expected value is 20 times 0.4, which would be 8. That's my expected value. If I wanted to find my variance, it's 20 times 0.4 times 0.6. Because it's 1 minus P. So it's literally these two numbers right here should always add up to the 1. It's the success times the failure, basically.
Is expected value.
No, expected value is just 20 times 0.4. Variance is 20 times 0.4 times 0.6
So N times P.
times 1 minus P, which is the opposite of P. So those two parentheses should always add to 1 if you add it together.
The variance was the success times.
It's the number, which is 20, times the success percent times the failure percent. which is 1 minus b. So in this case, my variance is 4.8. And my standard deviation is just the square root of that. Which in this case is 2.19. So those should all be able to be done. Those you shouldn't need a calculator for and everything else. Those are pretty straightforward, pretty simple to do. It's one of the reasons why binomial distributions are really nice. Oh, I'm like, why can't I see all the pieces to it? All right. Any questions with those two before we start doing some problems with them? Okay. Let's do a few. All right. So we have a random variable as a binomial random variable. N is 9 and P is 0.1. Okay. So what is the expected value? Exactly. Because it's just P times N, or N times P. So we had 9 times 0.1. Standard deviation. That's the square root of 9 times 0.1 times point what? Yeah, remember those two have to add up to 1. So 9 times 0.1 times 0.9, which is also actually 0.9. Okay. What's the probability that x equals 2? So this one we have to use that binomial distribution formula. So we go over here, n is 9, x is 2, and p is 0.1. So the probability of 2 successes is 0.172. Questions? That good? Okay. At most 3. They said they want to find the probability that x is at most 3. So which ones are we going to test? Almost.
0.
You also have to include 0.
That's where we add them.
Yep. So you're going to figure out 0, 1, 2, and 3, and then add them together.
And that's for the average.
Yep, everything else stays the same. So, 0.387.
Are you trying to show us that?
No, I was showing that. I'm writing the numbers on the other screen because, and then I'll switch over.
Oh.
It also helps me because when I switch over, I can look over here to see the screen still. But thank you. Sometimes I do forget to switch. And it says at most 3, so we want to include the 3. So we get 0.387, 0.387, 0.172, and 0.045. And then we add them together. And we get 0.991. Now remember, we only have a 0.1 or 10% chance of success, right? So you'd expect the numbers to go down the higher you get up there. You'd expect very few successes. That makes sense? All right. Let's do another one. All right. So how many of you have ever flown? How many of you have ever been bumped from a flight?
Thank God, no.
You're kicked off your flight because they've overbooked it. All
I
right.
used to live in Europe, so I fly back and forth. So thank God.
You haven't been. Wow. So typically, an airliner will sell more tickets than they have seats for. They will do this all the time because they have a high percentage of people who don't show up. I don't understand why, because you'd lose the money. So it doesn't make any sense to me. But they have a percentage of people who don't show up. I think a lot of it ends up being like business flyers and stuff like that. Could be. So they will overbook it. So a small commuter airline is concerned about reservations and no-shows. Assume their commuter plane will hold 15 people. Industry research indicates that 20% of the people making reservations will not show up for their flight. Okay, so if I can only have 15 people on my flight, so I still need to figure out my N, my X, and my P. What's my, so in this case, what is my probability of success? That'd be, what would success be in this situation? People show up for the flight, right?
0.8.
Correct. So my P is going to be 0.8, not the 20%, because that's they didn't show up, and we want success. We want that they showed up. Next thing is, my plane will hold 15 people. So is that going to be my, I always wait for the second one. Is that, is that going to be my N or my X? So in this situation, the number that I want that can fit on the plane is 15. N is going to be the number of reservations I booked. So no, because I always overbook. So X is going to be 15 in this situation. N is going to be my variable. N is going to be the thing that changes. Okay. So if I book 17 people on my flight, possibly, what is the probability that 15 will show up? Okay. So we go back to my Desmos. We put 17, 15, and 0.8.
Can you choose that number? Does it even end? Will it be, or will Hawk always give us?
They actually gave it to you in this problem. There was a list of questions after this thing. I just didn't copy the questions.
But you Hawk it wrong.
Yeah. So like, let's show you what this question looks like. This is what that question looks like. So if they decide to book 18 people, how often will be the least person will not get a seat? Yeah, those type of things.
Two problems for homework.
Yeah, and it's like 20 parts. Yeah, exactly.
So, are you doing binomial probability distribution?
Yeah. Yeah, because so binomial probability distribution means I have a success and a failure, right? Success means they showed up. Failure means they didn't show up. So that works. The probability that they show up is 80%. The probability that they don't show up is 20%. That's my probability for success, probability for failure. Okay. So if we put this in a Desmos, what did you get? Yeah. So 0.191. So if I only book 17 tickets, the chances of me having a full flight is 0.191, is about 20%.
That's also the same thing as the won't show up.
No. So the way that we did the problem, we said that there was 17 people. We booked 17 tickets, right? 15 people showed up for. What is the probability that 15 people are going to show up that day on that flight, and I'm going to have a full flight? Is 0.191. So there's only a 20% chance that I'm going to have a full flight if I book 17 tickets.
I mean, it's not that shocking.
No, it's not.
So I got stranded in Turkey once because my first flight was late, and my second flight, we literally got to watch it take off as we were sitting at the gate waiting for them to open the gate. And I got stranded overnight in Turkey.
That's not good.
No, it wasn't. It was not fun. So it's like I get it. I get not showing up for your flight. That was the only time I ever missed my flight take off. I say have 20 hours between each flight, so you never miss your flight.
Yes. You want to have a little bit of time between your flights, not necessarily that much time. But
I don't usually have that much time. I usually know the airports that I'm going to pretty well.
Yeah.
And I just kind of focus on that.
That sounds like my brother was flying up from South Carolina and he booked for Bradley. And his brother did get him to the airport on time. He got to the airport at 6:30. That's when they tell him you get there so that they'll time to get on the flight. So then he had to book another one to go to JFK and then go to the airport. He's supposed to get in at 8 that night. He got in at 1. Oh my God.
all right.
Airport in Green Bay, where my friend lives. I showed up like 3 minutes before my flight, like walked through the airport. Went to my flight. Back.
So what is the probability that one person will be bumped from the flight if I book 17 tickets? what would have to change?
X.
X is going to change to what? No.
Would that be like, if there's 15 spots, would it be 16?
Yes. My X is going to change to 16 because I want one extra person. So if I book 17 tickets, I want to figure out what the probability of 16 people showing up at my gate, because then I'm going to have to bump one person. And if you plug that in, you should get 0.096 if you round to 3 decimal places. So there's about a 10% chance or 9.6% chance that I'm going to have to bump somebody if I book 17 tickets. And if you book all 17 tickets, if there's a 0.023 probability that all 17 are going to show up. Okay. So a lot of times when you're looking at these, this is literally what an airline has to figure out. To figure out what's the best way to get a full flight. Okay. All right. The next type of problem this is used in is figuring out if things don't work. So if I'm going to try to figure out if something's defective or something's bad, can I check every single product? Okay. So when food comes in from overseas, we have the FDA. They have inspectors that have to inspect the food coming in. They can't check every box. They check a sample of it. If a certain percentage of that sample is bad, they reject the entire shipment. Okay. So that's in essence what they're doing here. They got to randomly take a sample and then they got to check that sample. And if it fails, then the whole shipment fails. So a company that makes traffic lights. Oh, talking about this one. Has anybody driven up Route 2 lately? Have you seen the purple lights? They're actually really cool. Like, I actually like them better than the bright white lights. They are defective. That's actually where I was going with this one. They're actually defective, and they're going to have to change them all. Yeah.
Like random purple lights scattered.
Yeah, they're all wrong. They're all, yes, they're defective lights.
Like there's two,
Like the one in Norwich, if you go
by
by
the fire station.
Yeah, there's one there and
I've been wondering if they were.
Yeah.
Like, I read somewhere once that like purple lights were for like
No,
to
I
stop
also
people
thought
from
you were talking about
shooting up heroin or something. And I'm
Uh,
like, why would they have food?
no, yeah, they're defective, and I'm like, I wish they would. I would like, especially like if you drive up Route 2, like before you get to Glastonbury, there's a ton of them, and it's like it's not as jarring when you're driving, but it's still bright enough that you can see. So I'm like, leave it alone. But they're gonna change it. Yeah.
It makes it so much easier when they're purple because it's already got the water on the road and it reflects. And
Yeah,
Okay.
and it's not nearly as bad. All right. So, sorry, it was just random things that make me think of things. So traffic can make buy switches from a supplier. Out of each shipment of 1,000 switches, the company has to take a random sample of 10. Let X equal the number of defective switches in the sample. A company has a policy of rejecting a lot if they find any defective switches in the sample. What is the probability that the shipment will be accepted if, in fact, 2% of the swatches are actually defective? So, if we're looking at this, I'm going to actually block out the bottom problems. There we go. So what's N, X, and P? So P is 0.02. So in this case, success will be if they're defective, right? Okay, what's N? Yeah, random sample. N is 10. But I can see where you would think the thousands. All right. They're going to reject it if any of them are defective. How many defective ones do we want? We want none defective, right? So they want to know if the shipment's going to be accepted, which in this case would be 0 defective things. So we want 0 defective. So N is 10, X is 0, and my probability is 0.02. So we got 0.817. So 81.7% chance that the shipment will be accepted.
Wait, are we plugging this into the?
Yep, into the binomial one.
I got yeah,
What'd you get?
I got 0.107. Yeah.
Hold on.
0.02 or 0. Oh, yep.
And then I lost my whole thing, so that's fine. Do you fix your problem?
Yes.
Okay.
Thank you. Make the same mistake.
And then sometimes there's a 0 afterwards that screws you up. So yeah, that's what you should have
I
done.
was like, looking
Yeah.
at the number. But that's on me.
But yeah, if you had like 20% chance, and yes, 10% would make sense. That there's a lot more failures in it. So, all right. Now, what was the second part of this question?
Here's the probability that the shipment will be accepted if the percent of defective switches is actually 5%.
Okay, so what would change in my formula that I just did? P is going to change to 0.5 or 0.05. So now we're only accepting 59.9%. So this was 81.7. This was 59.9%. So if the company decides to change their policy and will accept the lot if they find no more than 1 defective switch, how does that change my process? Huh? Okay, so do X as 1 for the 2%. What do you get? So does it make sense that they're now only going to accept basically 17% of the shipment? If they can accept 1? So what was the mistake we did? If it's no more than 1, what do we have to include? We have to do the 0 too. So that percent isn't going to be the percent. We have to add that to the 0% that I already got. So if you add the 0.167 to the 81.7, we now have a 98% acceptance rate. 98.4% acceptance rate. And if you do it for the 0.5, we're at that's a 0.315 to add to the 59.9, you're basically at like a 91% or 92% success rate. Okay. So you can start to see how you can use this formula to figure out actual things that you could be useful for and not just a crazy thing in a math class. Because these are things that are actually used. So it's like if you get in, the only thing I can think of at this one was like catheter tubes or something like that. About a shipment of catheter tubes into the hospital, if you pull out, say, 5 of them out of the thing and test them, and one of them has a hole in it, you should reject the whole thing, because obviously if one out of those 5 does, you probably don't want. So you could do little tests to figure out if the shipment is good without wasting the whole shipment. Because honestly, if one of those is bad, that could actually cause a lot of problems. So, yeah. So, okay. All right. We're done with chapter 7. That's all. Chapter 7 was just 7.1 through 7.4. So we will start with chapter 8 next week. Your test is the week after. I know a lot of tests were this week, so.
Do we have a picture?
No. They're actually, so I used to, because, well, I used to not have a midterm per se. I used to have 4 tests. So